Everybody. In this video, what we're going to look at is we're going to start taking the derivatives of logarithmic functions. So what we did last was we looked at the limits, right? We always look at the limits first. Now we're going to find those derivatives. So we're going to find those slopes of those tangent lines or those instantaneous rates of change. Now, what I've done here is I've just taken a screenshot from our content online here, and this is what's on your formula sheet. These are the derivatives we're going to take today. So I'm not going to derive them for you, but here they are. Okay, a couple of really important things here is what we're going to do today is we're going to take the derivative of natural log x. So the derivative of natural log x is 1 over x. So it's a nice, easy derivative. Okay, that's why we like it so much. Now, the line underneath tells us when we've got the derivative of a natural log of g at x, while all of a sudden it says, what is this? G prime at x over g at x. Well, this is us using the chain rule. So what you're really doing here is you're taking the derivative of the inside function. So the derivative of the outside function, which is ln x. Well, the derivative of ln x is 1 over x. So in this case, it's 1 over g at x, and then times the derivative of the inside. All right, just like that. Here, this is just a bit of fine notation. The derivative of the absolute value of ln x is 1 over x. The reason why we've got those absolute value bars there is whatever the input, the argument of a natural logarithm is, it always has to be positive. So if you happen to see absolute value bars there, don't panic about it. The derivative will still be the same. Now, we are going to look at one special exponential function as well here. And the special exponential is when we have a base that's not e. When we have a base that's not e, in this case, we just call it b, what you end up getting is the derivative is, you notice b to the x, well, b to the x again, but then you take the derivative of, you write the natural log of the base there, okay? If this was a more complicated function, then you would take the derivative of that function as well, okay? And then finally, friends, log base b. So now we're not looking at a natural log. And so when we have to take something that's the derivative of something that's not a natural log, it's a little bit more complicated. And so again, you can see whenever we've got this base of b, you're going to end up getting a natural log b in your answer. Again, refer to your formula sheet. That's why you have it when you're doing these questions. So here's all we're going to do. We're just going to go and apply these. Let's see how it goes. It's actually not that bad. So the first one says, let's take the derivative. Y is equal to the natural log of 2x cubed. Okay, no big deal. So y prime or dy dx. So the derivative of natural log. The derivative of natural log is 1 over my function, my inside function, times the derivative of my inside function. That's chain rule, right? So multiplied by the derivative of 2x cubed is 6x squared. And now all we're going to do is simplify that. And that'll end up being 3 over x. So this is why we like working with natural logs, is because taking the derivative of them is so easy. Okay, let's try another one. Y is equal to natural log x times x squared. So this is product rule. So we go the first, natural log x, times the derivative of the second, 2x, plus the second, times the derivative of the first. Derivative of natural log x is 1 over x. And now we simplify this. So we get 2x natural log x. I mean, if you want to put your argument in parentheses there, x squared divided by x, like that. And if you wanted to, you could factor out an x. And there it is. Okay. So again, the derivative of natural log, it's nice and easy, okay? And this one here, like the formula for this one here makes it look complicated, but again, all you're doing is going 1 over the inside function multiplied by the derivative of the inside function. So it's just chain rule. So taking the derivative of natural log just like taking the derivative of e is easy. And what makes it easy is because of the fact there's a base e in there. All right, let's try a couple more. So y is equal to the natural log of tangent x over x. Okay, so this is quotient rule. So quotient rule, bottom times the derivative of the top. Well, the derivative of the top, it's natural log. So I go 1 over the inside function multiplied by the derivative of the inside function. The derivative of tan x is secant squared x. Minus, I'm going to spill over into the next question here, minus the top, so ln tan x times the derivative of the bottom. Well, the derivative of the bottom is just 1, right? All over the bottom squared. Okay, let's start simplifying this thing here. Well, what do we really have now? Well, what I want to see here is I got 1 over tangent. Well, that's really cotangent, which is cos over sine. So, I mean, I'm just going to do a little bit of trig simplification here. Okay, so 1 over tangent is really cotangent, which is cos over sine. The reason I want to do that is because secant squared is 1 over cos squared. And so again, one of the things that'll happen is with these questions is it's not the taking the derivative part that can be tricky. It's sometimes it's the simplification that occurs afterwards. Why did I do that? Well, I see here that cos x and cos squared, so that simplifies down. And so what I have here is I'm going to rewrite, I've got x, I've got 1 over sine, well, that's cosecant x. And 1 over cos x is secant x, minus ln natural log of tangent x over x squared. Okay. This is where it can get tricky, just like you saw when you were taking derivatives of trig functions. You know, really, right back up here, we were done. We had taken the derivative, but it's the simplification that can get messy. And again, if you're looking at the answers in the textbook, you might go, whoa, that answer looks completely different than what I got. It's because of whatever simplification that they did along the way. All right? So just something to keep in mind. All right, let's try another one here. We're going to take the derivative of 3 to the exponent x5. Okay, so I scroll back up to my formula sheet, or I have it beside me, and this now is this. We're taking the derivative of an exponential where the base is not e. The base is something different. And so we get b to the x ln b. So we come back here. So what we're going to get y prime. The derivative of that is the function itself times the natural log of the base times the derivative of the exponent. It's that chain rule that we have to apply. So this will be 15 x4. Oh no, take that back. What is he doing? He's going crazy. He doesn't have enough coffee in him. Don't do it. I just did. That was really bad for a second, friends. So what are we going to get? We're going to get, I don't even know if I really want to rewrite this that much, but let's go 5. Usually we write that one out front like that, right? The polynomial usually goes out front, times ln 3 times 3x5. Okay. So you get a big ugly mess when you have to take the derivatives of exponentials that don't have a base of b or of e. Okay, let's try just one more. Okay, let's take the derivative, 2 more. Let's take the derivative of a logarithm. That's, again, it's not a natural log, it's a logarithm. So I come back up here, and it's this one. It's a logarithm. So here we go. The derivative of log base b of x is equal to 1 over x ln b. So let's try it. So this will be y prime is equal to 4. That's a constant. That's not getting in our way. Okay. 1 over the square root of x, natural log of 2. But now what we have to do is take the derivative chain rule. Take the derivative of that. Well, the derivative of the square root of x is x to the negative 1/2. And now we simplify, So 4 divided by 2 is 2. And natural log 2. And you see this x to the negative 1/2 is going to come down to the denominator and get multiplied with our other square root. Guess what we're going to have? X. There it is. Okay, so taking the derivative of a logarithm and not a natural log is definitely more difficult, right? It's definitely more difficult. So those are where you definitely want that formula sheet in front of you. Okay, last one. The derivative of y squared is equal to natural log x cubed minus y. Okay, here is where we're not able to explicitly get y by itself. So this is where we're going to have to do implicit differentiation. So I rewrite this while I'm doing it, 2y, but remember now when I take the derivative of y, I'm going to write y prime or dy dx. Okay, natural log. So the derivative of a natural log is 1 over the inside function times the derivative of the inside function. That's the chain rule right there. So 3x squared, and the derivative of y is 1. But what I'll see a lot of people write is just that. But wait. This is implicit differentiation. So it's not just 1, it's negative 1 dy dx, like that. Now what we need to do, just like we did before with implicit differentiation, is we have to isolate for dy dx or y prime, however it is you want to write it. So what we're going to have to do here is we're going to have to distribute and get rid of those parentheses there. So what we're going to have is 3x squared over x cubed minus y minus y prime over x cubed minus y, just like that. Okay, now what I'm going to do is I'm going to bring anything with a y prime to the same side. So I'm going to move all my y primes to the left-hand side. You can move them all to the right. We'll get the same answer, just our signs will be opposite of each other, just like that. And now we factor out that y prime. 2y plus 1 over x cubed minus y is equal to 3x squared over x cubed minus y. Now to isolate for y prime, we are going to have to divide everything by everything that's in our brackets there. But before we do that, we must get a common denominator. So once we get that common denominator, it'll be 2y x cubed minus y plus 1 all over x cubed minus y. Okay, this is a beast of a question, isn't it? Now what we're able to do finally is divide both sides by this beast. So we're going to divide this whole thing by this guy here. Remember, when we're dividing rational functions, to divide rational functions, we turn it into multiplication. We multiply by the reciprocal. This is the question that never stops going, right? So you can see how long these things can become. Okay, so now that, and then like that. Guess what happens here? I see two functions divide out, and I'm running out of room, so I'm just going to go sideways. After that big, ugly mess, look at what we end up with. There we go. Okay, so implicit differentiation, just like before, can be ugly. Look at all that work we just did, right? That was a lot. So again, your derivative laws are on your formula sheet. It's just really about recognizing which one of them you're going to use and applying it, just like that. Okay, friends, I hope that helped. I'll see you next time.